Okay, so in this next video, we're going to do root locus plotting. But we're going to do root locus plotting by the rules. I'll say the rules. And if we do it by the rules, then we don't have to, you know, solve the characteristic equation every single time that we do this. Okay, so we can plot more complicated things a little bit quicker. So there are 12 steps to the rules on your formula sheet, and I'm going to talk about them as we go through an example. So in this example, I have my GH equal to K over S times S plus 3 times S plus 9. Okay, and you might recognize this as the same question that I did Bode plots and Nyquist plots for. Now, rules 1 and 2 say that when K is 0, the closed loop poles coincide with the open loop poles, and for K equal to infinity, the closed loop poles approach the open loop zeros. This tells us that we should find out what these open loop poles and zeros are to begin with. So our zeros we like to represent by Z, and our poles by P. So our open loop poles are 0, -3, and -9, because those are the values that make that denominator go to 0. And I can easily just solve the brackets, because if any bracket goes to 0, the whole denominator goes to 0. So those are my poles, and I'm going to say the number of them is 3. Okay. Now for my zeros, I don't have any explicit zeros, so therefore they must all be at infinity, and there has to be the same number as there is poles, but we don't count the infinity zeros when we do the count. So I'm going to say I have 0 like explicit poles, but I do have 3 that are sneaky, and they're at infinity. And that's because, as Rule 3 says, there are as many branches as there are open loop poles. The branches start at K equal to 0 and at the open loop poles, and they end at K equal to infinity at the open loop zeros. This is why if we don't have an explicit number for Z, they have to be at infinity. And so Rule 4 says if there's less open loop zeros than poles, those branches for which there are no open loop zeros left go to infinity along asymptotes. And they tell us that the number of asymptotes is equal to the number of open loop poles minus the number of open loop zeros. So I know right away my number of asymptotes is going to be n minus m, which equals 3. Minus 0 equals 3. Okay, so I know I should have 3 asymptotes. Now, Rule 5 says that the direction of the asymptotes is found by this equation. 2i plus 1 over, eraser here, over n minus m times 180 degrees. And it starts at 0, 1, 2, etc., etc. So it's just increasing integers. And so how you use this equation is I start with I equal to 0. I'm going to find that I get an angle of plus minus 60 degrees. Now I know I need 3 asymptotes, and that only gives me 2. So I'm going to do this again with I equal to 1, and I'm going to get asymptotes at plus minus 180, which is the same thing. So this gives me my 3 asymptotes. Okay, and then I don't have to keep going with I. And even if you did, you would find that the angles just keep repeating, right? So now I have to find rule number 6. Where do the asymptotes intersect? So the asymptotes intersect at a point at a point on the real axis. At a single point on the real axis, all the asymptotes will intersect. And so to find this, it's the sum of the open loop poles minus the sum of the open loop zeros divided by the number of open loop poles minus the number of open loop zeros. So if I add up all these poles here, I've got 0 minus 3 minus 9 gives me minus 12. I don't have any open loop zeros explicitly, so I just say subtract 0, and then n minus n is 3. This works out to minus 4. Okay. Now we also know rule number 7 says the root locus is symmetrical about the real axis. And that's because when you get into an imaginary components, you always have the plus minus j. Sections of, now rule 8 is a bit strange. So let's get some of our plots drawn in here before we look at rule 8. So let's put some of the information that we found already on this plot. We know that we have our open loop poles at 0, minus 3, and minus 9. We know that we have an asymptote intersection point at minus 4 here. And we know that our asymptotes are at plus 60 degrees, minus 60 degrees, and minus 180. So those are the asymptotes, and they're just guidelines that the root locus is going to follow. What rule 8 says is sections to the left of an odd, sections of the real axis to the left of an odd number of total open loop poles and zeros on this axis form part of the loci. So what that means is when I'm drawing this, I go to the left of the first thing and I keep drawing till I hit the next one. Then if I go to the left of that, I'm to the left of 2, and that's even. So then I don't draw there. And then I go to the left of the third, and since that's odd, then I draw. So this part of the locus just goes off to infinity, okay? Now, these two poles, like they can't just end at each other, right? Because remember, rule 3 says that branches start at k equals 0 at the open loop poles and end for k equal to infinity at the open loop zeros. And remember, the open loop zeros, since we didn't have any explicit ones, they're at infinity, which means these plots will break away and follow the asymptotes off to infinity. Okay, so they'll follow the asymptotes off to infinity. I shouldn't really draw these as squiggly lines. I usually do this when I'm drawing with pen so that I can make sure everybody can see them, but since I'm drawing in color here, I'll just draw it with actual lines. Okay, so at k equal to 0, we're at these poles, but by the time k equals to infinity, we're off to infinity somewhere. Okay, now the important thing about this plot is notice that at this point right here, we crossed over into the positive real axis. So at some value of k, we will actually go unstable. And we can find that value of k by, and to think about how we find this, notice that where we cross over is where we don't have any real component and we're purely imaginary because we're crossing the imaginary axis, and our real component at that time is equal to 0. So if we take our characteristic equation, which is s cubed plus 12s squared plus 27s plus k equals to 0. So to get that, I had to take our 1 plus gh equal to 0. Okay. And actually, let me work that out for you. I'll erase this. Let's start at the beginning here. So that gives me 1 plus k over s times s plus 3 times s plus 9 equal to 0. I will multiply top and bottom by the denominator so that I can, or multiply both sides by the denominator so that I can get rid of the fraction here in the equation. And then I'm multiplying through on this. So this is going to give me s cubed plus 12s squared plus 27s and still plus k equal to 0. Now, since we know that the crossover point is where we're purely imaginary, I can set s equal to j omega. So it will be purely imaginary. And if I do that, I get j omega cubed plus 12 j omega squared plus 27 j omega plus k equal to 0. Now j cubed is equal to minus j, so I'm going to get minus j omega cubed plus j squared is minus 1, so minus 12 omega squared plus 27j omega plus k equals 0. And now you can see that the only thing here is real and imaginary components. So we have imaginary components here, and the other components are real. In order for the whole thing to go to 0, both the real and imaginary components separately must go to 0 because they can't cancel each other out. So if I gather up the real components, I have minus 12 omega squared plus k. And if I gather up the imaginary components, I've got minus j omega cubed plus 27 j omega. Okay, and I can factor out this j to get minus omega cubed plus 27, wait a minute, 27 omega. Okay, so both of these things must go to 0. So this must go to 0, and this bracket must go to 0 in order for the whole thing to be 0. So I can solve the first equation to find that k is equal to 12 omega squared. And I can solve the second equation. And first, to solve it, I will factor out, well, I'll set it first. So it's minus omega cubed plus 27 omega equals 0. I can divide both sides by omega, and 0 divided by omega is still 0. So I'll get minus omega squared plus 27 equals 0, which leads to omega squared being equal to 27. Then I can take that value and sub it into here to find that k equals 12 times 27, which is 324. So that gives us the value of k for which we will go unstable. Okay, and if I scroll back up to remind you, that is the value here at this point. K is 324 at that point. Okay. Alrighty, so I'll stop this example here, and then I will make another example.